Hi, this is section 5.5 on polynomial and rational inequalities, and our objectives for this section are going to be to solve polynomial inequalities and to solve rational inequalities. Why don't we review a little bit so we can talk about the differences between polynomial and rational inequalities before we start our first problem. So when we're talking about polynomial inequalities, we're basically going to be referring to polynomial functions, right? But instead of an equal sign in there with a polynomial function, we're going to be using an inequality. And our polynomial functions, if you recall, had variables that are in the numerator with whole number exponents. So they look something like this. This is an example of a polynomial inequality. Rational inequalities, if you remember, when we're working with rational functions, we basically had a fraction, and we usually had something like with a fraction that had a variable in our denominator, or it could also be in the numerator, like this one. And now, instead of just working with rational functions, now we're going to be working with rational inequalities. So they're going to involve having an inequality in them. So look at the differences between these two. It's important that you're able to look at these two different types of inequalities, and you're able to distinguish between them so that you know which technique you're basically using for each one, because they have a slightly different approach, right? The way we approach a polynomial inequality and a rational inequality. They're similar, in the way we're going to be solving them, but just, it's nice to have an idea that the pictures of the graphs, right, are slightly different. And as for polynomial inequalities, what we're going to be doing, we're going to be learning them to solve these two different ways. Actually, these two different ways, they apply both to rational inequalities and polynomial inequalities. One method that we're going to be using is we're going to be solving these graphically, and the second method is going to be algebraically. So it's like we're using a graphing method and an algebraic method to solve these. And so, like I said, these two methods, we can use them not just with polynomials, but also with rational inequalities as well. So I'm just going to go ahead and adjust this, modify this a little bit. So it says both, for both of these types of inequalities, we're going to be using these two methods for solving polynomial and rational inequalities. Okay, we're going to start off with the graphing method for solving polynomial inequalities first. So let's talk about that. So when we're solving something graphically, more specifically a polynomial inequality, what we're going to be doing is we're going to be imagining the polynomial part as if it were a polynomial function. We're working with a lot of polynomial functions, so we should feel pretty comfortable with polynomial functions by now. Remember, when we're working with polynomial functions, so we're talking about like end behavior. And if we had something that looked like basically like y equal to x raised to an odd power, or where the leading term had a positive x raised to an odd power, would look something like this first graph. The second one, if it had like y equal to a negative x raised to an odd power, would look like the second graph. And if it had y equal to a positive x raised to an even power, it looks something like this third graph. And if it had y equal to a negative x raised to an even power, then it would look something more like this fourth graph. So this is what I would call the end behavior of how a graph of a polynomial behaves. So it's nice to know or have an idea of what that polynomial is going to look like, right? When you're first looking at the polynomial function. So you should have this memorized. This should be in your brain, engraved like the back of your hand. Note like the back of your hand. All right, I think we're ready to go ahead and get started on number 1. Okay, number 1 says solve the inequality f of x is greater than 0 by using the graph of the function f of x is equal to x minus 1 times x plus 3 quantity squared. Now notice that this first factor here, this x minus 1, has a x to the first, and then the whole quantity is raised to the first. And the second factor part here has x to the first, and then it's been raised, all that whole binomial is being raised to the second power. So if someone were to ask me the degree of this polynomial, I would imagine, oh, it's like x to the first times x to the second. So this is going to behave like x to the third, or y equal to x to the third. And it's a positive. It's going to end up being positive because there's no negatives in front of those x's. So the end behavior of this function is going to look something like this. It's going to come from down and it's going to work its way upwards. Because it's a third degree, I know it can have at most 2 turning points. Normally, I would draw this as a sketch here. This is what would be going on in my brain if it's something raised to an odd power. But because it's something raised to the third degree, I could probably be a little bit more specific here in the end behavior and imagine something like this top graph that I drew here going on with the 2 turning points. So that's probably going to be a little bit more similar to what the actual graph is going to look like. So now that we know what the end behavior of this function is going to look like, why don't we go ahead and get started here? Now, I'm going to do a lot of explanation before I actually get started with the actual solving of this problem, because I really want you to understand this to a more deeper level, a better, a stronger understanding of what we're doing here. So when it says f of x is greater than 0 and that f of x is equal to this, polynomial function, we can basically replace the f of x here with everything that we have here in the red cloud with the x minus 1 times the x plus 3 quantity squared and set that greater than 0. Notice it's greater than. It's strictly greater than. There is no equal sign. So it's also very important that when you're solving these polynomial inequalities that you take note of the inequality. Is it strictly greater than? Is it strictly less than? Does it have an equal sign in there? That matters. And it's also good to have the f of x written on the left-hand side, because when we read inequalities, we read them from left to right. So it's easier for me to say this is saying f of x, when is f of x greater than 0, right? So notice that I always like to put my function on the left-hand side, so that when I read it out loud, it makes more sense to me. So basically what this inequality is basically asking for, when is this function greater than 0? Now, I know for some people that I just said a bunch of Greek stuff there or something you just didn't understand, something with an entirely different language. I'm going to try to say it in several different ways for you to understand me. Another way I could say this is, when are the y values of this function greater than 0? How about that? For some of you, that might resonate a little bit more. When are the y values greater than 0? Okay, now I'm going to highlight the y equal to 0 line here, or the x-axis, and then I'm going to highlight the area above it, because I'm trying to show you everywhere where the y values are going to be greater than 0. Everywhere that I highlighted in yellow, the y values are going to be strictly greater than 0. Notice that I highlighted the x-axis green because everywhere on the x-axis y is equal to 0, and that would not be strictly greater than 0. So the y values are positive above the x-axis only. So when is this function above the x-axis? right? That's basically what we're asking for here when you're trying to solve this graphically, when you're trying to solve this inequality using the graphing method. So I've tried to phrase this lots of different ways. Now, when you use the word when, you're basically saying which x values are going to produce, or if you don't like the word produce, let me use a couple other words. How about create, or generate, or give me y values that are going to be greater than 0. You know, the more times we write this stuff out, the more times we say it out loud, the more this is going to start to make sense to us. I know not everybody's getting this. This is one of the toughest topics I always have when I'm teaching this in class, to really get students to understand this idea. But we're going to try to write it out several times in lots of different ways and say it out loud to yourselves. And hopefully it's going to start to sink in more. Now, I'm just going to go ahead and I'm just going to put this entire thing over, move it over to the side. And because this isn't the actual part that I would use to, you know, figure out the answer. This is the part that's going on in my brain. You know, when I'm trying to show you what's going on inside my brain, that's what's going on inside my brain. That's what I'm thinking about. That's what I'm asking myself in my brain. But what do I actually show on the piece of paper to do the problem, to get the answer? That's what I'm going to show you now. All right, so first I would set each one of these factors equal to 0 to get what we call those critical numbers or critical values. And I'm also noticing how I'm circling the exponent on the factor, because that's important, because that determines the type of multiplicity that it has. So when I set x minus 1 equal to 0 and I solve, I get x equal to 1. And because this is raised to the first power, at this x-intercept, right, we've got this factor has odd multiplicity. And that means that at this x-intercept, something's happening, right? What does that mean when you have odd multiplicity? Do you remember? We talked about this in a previous section. This means that it's going to cross the x-axis. The function is going to go across the x-axis at this point. So that's what odd multiplicity of a factor means. Notice the next factor, x plus 3. When I set it equal to 0, notice I circled a 2 on the exponent, because that means it has an even multiplicity. So when I get x equal to negative 3, I know the x-intercept that's associated with that is going to be negative 3 comma 0. And I know it has even multiplicity. And what does that mean? That means it's going to touch, like just touch at the x-axis, or another word we like to use, it's going to be tangent at the x-axis. Or if that word still doesn't resonate with you, how about it bounces, like it bounces off the x-axis, like it hits it and it bounces back off, something like that. You need to make sure that in your notes you're writing down words that make sense to you, and they're going to help you understand what you're learning. So how about I put this in parentheses? I'll put bounces off, but the textbook likes to use the word touches, but other textbooks I've seen, they like to use the word tangent most often. So I'm going to say it's touches or it's tangent at the x-axis at this point. But if the word bounces off kind of helps you understand what's going on there, then why don't you write that in your notes to help you remember? So I already know it's going to look something like this, my graph. So I'm keeping this picture in my mind this whole time as I'm drawing the sketch. Let's go ahead and plot our x-intercepts. We have one at negative 3 comma 0, and we have one at 1 comma 0. Okay, now I got to make my graph look like this. Remember, at 1 comma 0, it's crossing the x-axis, and at negative 3 comma 0, it touches, or it's tangent, or it bounces off at that point. So here comes my function bouncing off of -3, and then it's coming back up and it's crossing. It's going to cross at x equal to 1. So this is just a sketch of the graph. Notice I'm not being very accurate here with this graph. It's just a quick sketch because we're going to use the graph to solve the inequality. They did not ask us to graph this, right? They said solve the inequality, right? By using a graph. So the graph, once again, is a sketch. We're looking at the graph to see where is this function greater than 0. I highlighted in yellow where the function is greater than 0, where the function is above the x-axis. This is where the function is strictly greater than 0. Notice that I tried not to highlight the x-intercept, because if I were to highlight the x-intercept, then that's where it equals 0. Notice I'm highlighting in blue the x values that produce those y values. So that's what your answer is going to be, the blue highlighted part, because these x values are the ones that produce positive y values. If I input these x values into the function, I will always get y values that are going to be greater than 0. So I'm going to write down my answer now. My answer is going to be the open interval from 1 to infinity. All of those x values will produce positive y values. Or I could say the set of all x such that x is strictly greater than 1. So that would be my answer for number 1. Now, you can also use your graphing calculator to check this, right? So let's go ahead and use our graphing calculator now to make sure that we check this solution so that we can, double check our work. I don't think it's a good idea to rely just solely on the graphing calculator. I think it's important that you know how to do the work on your own. But it's important that you also know how to use the graphing calculator, right, to check your work, right? Or sometimes we need to use it because there's some problems that are just too difficult to do by hand. So let's go to the graphing calculator. We're going to substitute our function. For y sub 1, we're going to substitute the function that we were given. So we're going to put this as y sub 1 is equal to x minus 1 times x plus 3 quantity squared. Let's go ahead and graph it and see what we get. This looks a lot like my graph that I came up with my sketch. Now, if we go to the table of values, we can see here the x-intercepts, -3, 0. That's where y is equal to 0. So that's where one of my critical values was at -3, right? 1, 0, where y equals 0. So that means 1 was the other critical value. And you can also see by looking here at the graph, here's 1 right here, and that looks like it matches up with that x-intercept. And then you could also see the -3 one right there where it bounces off. Now let's say I wanted to find this another way. I could also use the calculate. I can go second calculate to find a 0 to help me get that critical value. So if it says left bound, I've got to be on the left hand side of the 0. And then right bound, I've got to be on the right hand side of the 0. And then press enter again. We get x is equal to 1 and y is equal to 0. So there you go. Now there seems to be a problem over here when I tried to do this calculating 0 for the part where the graph bounces off, or the part where the graph of this function is tangent at x equal to -3. I tried doing the exact same thing to calculate the 0. And I went, I got the left bound, I got the right bound, I went on the right hand side of it. And for some reason, when I tried to do the guess, it said error, no sign change. I don't know if it's essential that there has to be a sign change that has to go from like positive to negative or negative to positive, like in terms of the y values, that it has to go like across the x-axis in order for you to be able to use this calculate function here for the 0. So unfortunately, I wasn't able to do it that way, but you can go to the table and we were able to find the 0 on there. You know, it depends on the function, you know, how easy that might be to do it this way. But once again, ultimately, I think it's always good to know how to do this by hand. And once again, the calculator is like a method to check your work, but it's not something that you just want to just rely blindly, you know, and just be entirely dependent on. You want to know how to do these problems on your own as well. All right. Let's go on to the next problem. What do you say, huh? This is too much fun. Let's keep it going. Number 2, solve the inequality r of x is less than 0 by using the graph of the function r of x is equal to x all over x minus 1 times x plus 2. First step is we're still going to do what we did before. We're going to basically replace here our r of x with that entire function that r of x is equal to. So I'm going to write, I like to write that function part first, because when I read things in math, I like to read things from like left to right. It makes more sense to me. So I'm going to write x over x minus 1 times x minus 2 is less than, you know, now that I'm looking at this, instead of doing strictly less than 0, why don't we change this problem? Because the last problem we did was strictly greater than. I don't want to do a strictly greater than and then a strictly less than. Let's do one that's less than or equal to. All right, how's that sound? That sounds good for everyone? Yes? Okay, good. I'm glad you guys agree. So we're just going to change this problem so that you have an example with one that was strictly greater than, and then we could do one that is less than or equal to, so you have an example of each in your notes. Because I know that's nice. That's nice when you have an example of each type, you know? You know the difference, you know? Why is this one different than the last one? So we're just going to change this to less than or equal to. All right, that looks much better. I like that problem a whole lot more now. Yes, excellent. All right, so now what we're going to do is we're going to find what we call those well, we're going to graph this. Yes, we are going to graph it. So when I graph these, the first thing I always like to do with these rational functions, I like to find the domain. In finding the domain, oftentimes, this just is what the equations of the vertical asymptotes of this rational function end up being. So here, x equal to 1 and x equal to -2, not only are these restrictions on the domain, but these are also the equations of our vertical asymptotes. So I'm going to use those to help me graph this function. And I'm also going to look to see if there is any horizontal or oblique asymptotes. I can tell that here we have basically x to the first over x to the second. And since 1 is less than 2, that means we're going to have a horizontal asymptote at y equal to 0. I'm going to go ahead and graph these two. Well, actually, there's 3 here, right? 2 vertical and then 1 horizontal. I'm going to go ahead and graph these asymptotes so they can help me in creating this graph, the sketch of this graph. So let's go ahead and do that. I apologize. I'm such a perfectionist. You know, I can't help but like when I look at these, if these don't look evenly spaced out to me, I will keep trying to draw them until they look nice to me, until I'm happy with them. So you guys are just going to have to forgive me for just trying a little bit too hard here. I should just go easier on myself and just deal with it, and whatever I draw first, I should just be happy with that. But oh my goodness, look at how crooked this vertical asymptote looks. Oh, this is terrible. I'm sorry here. I should have edited this all out. I think that one looks worse. Anyways, we're just gonna leave it like this because I could spend all day trying to make these look perfect, and they're never gonna look perfect, right? So we're just gonna leave them like this before I keep going on making a mess. And notice how I like to label these with the equations. That looks nice. Okay. Now we're going to find any x-intercepts. So to find x-intercepts, we're going to replace the y part with a 0. We're going to use, instead of an inequality, I'm going to use an equal to, because I'm solving this equation to see if I can find where this rational function has any x-intercepts. So if I were to solve this rational equation, I'm going to multiply through by the LCD to the left-hand side and the right-hand side. On the left-hand side, you can see that these will divide out and they'll cancel out, and we'll just have x is equal to 0, because 0 times anything is just going to be a 0. So this means we have an x-intercept at 0, 0. That also happens to be a y-intercept. So now it's like I killed 2 birds with 1 stone. I got the x-intercept and the y-intercept. That was pretty cool. And there's no other y-intercepts that I have to look for because it's a function. If there was another y-intercept, then this would not be a function. Let's come up with a few points to help me sketch this graph. So looking here, I'm going to choose values that are like in these different intervals here in between these asymptotes. How about -3, -1, and then there's my x-intercept, my y-intercept. And how about here we choose 0.5, and over here we'll choose 2. I like those values. Let's use those. Let's plug those in. Let's see what we get. I'm going to just go ahead and do this on the calculator so you guys, so I'm just going to write in the answers, okay? I know you guys already know how to do this. So you're going to basically find f of -3, f of -1, f of 0.5, and f of 2. All right, go ahead, do it in your calculators. If you need to push pause, you could do it yourself, but I'm just going to write the answers. -0.75, 0.5, and then we got here -0.4 and 0.5. Now the sign of the number matters, whether it's positive or negative, because that tells us whether the point's going to be above the x-axis or below. The first one's negative, second one's positive, third one's negative, last one's positive. This tells me when it's negative, it's going to be below the x-axis. Maybe I should write that all out. Below x-axis. When it's positive, it's going to be above the x-axis. There I go. There I wrote it out. And the negative is below the x-axis, and then positive will be above the x-axis. Let's go ahead and plot these points, and this should probably be enough information now for us to get a good sketch of this graph. All right, let's start off with that -3, -0.75. So I'm going to go ahead and say, well, why don't I first draw where I think -1 is on the y-axis. Let's say -1 is right there. So -0.75 is about it is equal to actually exactly -3/4. So let's go here to where I believe -3/4 would be at. And then there, and then let's plot the other point. I guess I moved ahead a little faster than I expected. Now, because I already know that it's not going to cross the x-axis anywhere, and it definitely cannot cross the vertical asymptotes because otherwise it would be undefined. We know that when I got this point right at -3, -0.75, we know it cannot go above the horizontal asymptote or to the right of the vertical asymptote. So this is what the graph is going to look like right here. It's going to get very close. And then in the middle, in between the two vertical asymptotes, it's going to look like this. And then this one is going to look just like this. I know it cannot cross those vertical asymptotes. And because I already went through the trouble of finding the x-intercepts, and the only one I found was that 0, 0, it can't cross anywhere else on the horizontal one. So there's my graph. I'm looking to see where this is less than or equal to 0. So I'm going to highlight in yellow everywhere it's less than or equal to 0. So now I'm going to highlight in green the x values that produce those y values, because that's my final answer. So it looks like my final answer here is going to be the open interval from negative infinity to -2 union half closed interval from 0 to 1. And if I wanted to write that in set builder notation, that would be the set of all x such that x is strictly less than -2, or 0 is less than or equal to x and x is less than 1. So we could write our answer either one of both ways there. Let's go ahead and try putting this function or this inequality, well, it's an inequality, but we're going to put the function into our graphing calculator, right, to double check to make sure that we came up with the correct graph of this function that we're getting the answer from, right? Remember, the solution that we got here, we weren't asked to draw a graph. We used the graph to come up with our solution, right? And it's just values of x, right? So even though we use this two-dimensional graph here, which was really cool, you know, to draw the solution, it wasn't asking for that graph, right? We just wanted the answer in terms of x, like what are the x values that are going to make this inequality true. So yeah, let's go ahead and put this into the graphing calculator and see what we get. So let's type in our function. There is our function. Yes. Let's graph it and see what the graph looks like, and hopefully it looks like ours. Yes, it does look like ours. Excellent. I could use the table of values maybe to try to figure out where these vertical asymptotes are at, if you can't tell really. So if I went to go to the table, notice what it has here at x equal to -2. What does it say for the y? At x equal to -2, it says y sub 1, it says error. That's because it's undefined at x equal to -2. That's because we have a vertical asymptote. And the same thing is happening at x equal to 1. It says error, but it's because I know there's a vertical asymptote there. So just in case you don't know exactly what those values are, you might be able to get those by going to the table of values to find those values for the vertical asymptotes. Okay, and I can see here where it goes underneath the x-axis, where it's going to be, because remember it said where's this less than or equal to 0, where's this function? So you can tell by looking here at the graph where the graph is going to fall below the x-axis. Yes. All right, that was a good problem. Let's go on to the next one. All right, steps for solving polynomial and rational inequalities algebraically. Step 1, write the inequality so that a polynomial or rational function f is on the left side and 0 is on the right side in one of the following forms. F of x is greater than 0, f of x is greater than or equal to 0, f of x is less than 0, and f of x is less than or equal to 0. Notice it says f is on the left side, right? It makes it so much easier, I think, you know, when you're reading a function and the function's on the left, and then you can read the inequality, right? And then the 0 is going to be on the right. I think it just makes it a whole lot easier that way. For rational functions, be sure that the left side is written as a single quotient. And last but not least, find the domain of f, right? And these are we're still working with our inequalities, right? All right, let's go ahead and get started. Oh wait, I didn't do step 2, right? Step 2, well, we said find the domain of f, very important. Step 2, determine the real numbers at which f of x is equal to 0, and if the function is rational, the real numbers at which the function f is undefined. So those are going to be what I like to call critical numbers. Sometimes people call them critical values, or some people call them critical points. We're going to call these these real numbers, we're going to call them critical numbers. Or values. Step 3, use the numbers found in step 2 to divide the real number line into intervals. So we're going to create a number line and use the critical numbers to basically divide our number line into intervals. Step 4, select a number in each interval and evaluate f at the number. I'm going to call these numbers our test points. If you want to call them your test values or your test numbers, that's fine. I tend to oftentimes call them test points. They're not ordered pairs, but I think that's the way I was taught. Like whoever taught me must have used the word point, so I still like to use the word point. They're just values that we're testing. And then if the value of f is positive, then f of x is going to be greater than 0 for all the numbers x in that interval. If the value of f is negative, then f of x is going to be less than 0 for all the numbers x in that interval. And if the inequality is not strict, right, that means greater than or equal to or less than or equal to, include all the solutions of f of x equal to 0 that are in the domain of f in the solution set. Be careful to exclude values of x where f is undefined. So we just got to be very careful about that. All right, I think we're ready to do these problems. Let's go ahead and do number 3 here. Solve each inequality algebraically. X cubed plus 2x squared minus 3x is greater than 0. Strictly greater than 0. Because we're solving this algebraically, right? We're not going to do a graph, but you could use a graph, right, to double check your work. I'm going to treat this first part as our f of x, and it's already on the left-hand side, so I don't have to do any work because it's already there. It's on the left. Didn't have to move anything around. And our 0, it's already on the right. And then my inequality, I can just read it from left to right, right? It just says, when is f of x greater than 0? Strictly greater than. So we're ready to move on to the next step. So our first step is we're going to find our critical numbers, right? So in order to find the critical numbers for this, we're going to take the f of x portion and we're going to set that equal to 0 to find the critical numbers. Now this is a polynomial function, okay? I want you to keep in mind there, when we're finding these critical numbers, our step 2 and our steps up here, it says you find the real numbers at which f of x is equal to 0, right? Or where it's undefined. But the domain for all polynomial functions is always going to be the set of real numbers, all right? So once again, let me repeat that. The domain for all polynomial functions is always all the reals, all real numbers, right? Open interval from negative infinity to infinity, or the set of all x such that x is an element of the set of real numbers, all right? All polynomial functions, they're continuous everywhere. They're what we call like nice functions, right? Because we don't have to worry about them not being defined somewhere. They're defined everywhere because they're continuous everywhere. So we're only going to focus on where f of x equals 0. That's always going to happen when you're working with polynomial functions. So we're going to set x cubed plus 2x squared minus 3x equal to 0. And I'm going to solve this polynomial equation. So in order to solve this polynomial equation, actually first, let me start off by calling this step 1. I know it says step 2 in my order of stuff up there, but there's just so many steps up there. I'm going to call this my official step 1. All the stuff that I did like above here, like all this thinking out loud part, that's stuff that's going on in your brain, like in the background. But the actual writing portion to get the answer, I think that we need to do is here. The first step is the finding the critical numbers part. Let's factor this. I factored out a GCF of x. I need two numbers I multiply to give -3 and add up to give 2. I got 3 and -1. Because this trinomial has a leading coefficient of 1, I can go straight to the factors. But if you need to do factoring by grouping, then you do factoring by grouping. I'm going to set each one of these factors equal to 0 x equals 0, x plus 3 equals 0, and x minus 1 equals 0. And then I'm going to solve each one. The first one's already solved, x equals 0. The second one, if I subtract 3 from both sides, I get x is equal to negative 3. Third one, add 1 to both sides, I get x is equal to positive 1. All right, what we found here, we got 3 critical numbers. So my critical numbers for this are going to be x equal to negative 3, 0, and 1. Now, what are critical numbers, you're asking? The critical numbers for polynomial functions are just the x-coordinates of the x-intercepts. That's basically what they are, okay? So when you set a polynomial function equal to 0 and you solve, it's like you're finding the x-coordinates of the x-intercepts. Am I right? Yeah. So we're going to take, like, imagine like if you were doing this graphing, the graphing method, right? We're going to take a one-dimensional number line and split it up using these x values. This is going to be our step 2. We draw this number line part. So step 2 is going to be create a number line. With critical numbers. And we're basically going to use those critical numbers to divide the number line and create intervals. And then we're going to choose test points within those intervals. Or tests. I'm gonna call them test values because I don't want you to think we're talking about like an ordered pair. It's just one value that I'm plugging into the function, right? So I'm gonna call it test value. All right, so let's go ahead and draw my number line. Here it is. Let's divide it up using our critical numbers. So the first critical number is going to be at x equal to negative 3. So let's go ahead and divide this. Let's call that negative 3. Let's call this 0, and let's call this 1. I'm going to draw like little dashed lines to divide these intervals up. Notice that when you have 3 critical numbers, it divides your number line into 4 intervals. That means I need to choose 4 test values. So I'm going to choose 1 on the left-hand side of negative 3. How about negative 4? You can choose any numbers you want. Try to choose easy ones because you're going to have to plug them into the inequality. I'm going to choose negative 1 here. I'm going to choose 0.5 here. And I'm going to choose 2 here. Now we're going to take each one of these numbers and we're going to substitute it into the inequality. You could use the original inequality. You could use the inequality that was partially factored out. Or you could use the inequality that is the one that's the most factored out. All right? It's your choice. I'm just going to make this a little bit smaller so I have a little bit more space. As for me, I think I'm going to use the inequality that is like fully factored out. Okay? Like I said, it's your choice. If you want to use the original inequality, that's perfectly fine too. I think the one that's factored out is sometimes like easier to work with because sometimes you can see what the answer is without having to work the problem out all the way. All right, and I'm going to try to explain that as I'm doing this problem so you can see what I'm talking about. I'm sorry, you guys. Once again, you guys know I'm a perfectionist. I'm just trying to make this look like set up nicely and organized. One of my faults. I can't help it. I like things to look nice, neat, and organized. All right. Okay, let's start substituting these values in. Let's start off with x equal to that negative 4 value. I'm going to substitute x equal to negative 4 into the factored form of my inequality. So I'm basically going to rewrite that x cubed plus 2x squared minus 3x out, but I'm going to rewrite it the way it looks when it's all factored out as x times x plus 3 times x minus 1. All right, so that's what I'm going to do right here. So x equals -4, and we're substituting into the factored form. So I'm going to use once again, the one I factored out, but in terms of an inequality, not the one with the equal sign, right? We want the one with the inequality. So it's going to be x times x plus 3 times x minus 1, but I'm going to put in the greater than inequality equals 0. All right. Now I'm going to substitute -4 every time I see an x. So this is going to give me -4 times -4 plus 3 times -4 minus 1. And we're going to see if this is greater than 0. I don't know if it's going to be greater than 0. We're just trying to see if it comes out true or false. All right. So let's try this. -4 times -1 times -5. Like, I can already tell this is negative times a negative times a negative is going to give me a negative number. And I know a negative number is not going to be greater than 0. So it's going to be false. But I worked it out all the way to -20. If you guys can tell already that's going to be a negative number, you don't have to work it out all the way. As soon as you can tell it's false, you can move on. We do not want to include that interval in our solution set. Next, we're going to substitute x equal to -1. So once again, I'm going to use the factored out form of that inequality. So it's going to be -1 times -1 plus 3 times -1 minus 1. And we're trying to see if this is greater than 0. So -1 times 2 times -2, that's going to give me a +4. And +4 is greater than 0. It's true. Whenever you get a true statement, you do want to include that interval. So we said we don't want the first interval. We do want the second one, right? Now, as for the -3 and the 0, because it was a strictly greater than, I do not want the -3 and 0, because if I plug those in, those are going to give me values of 0, right? So I'm going to draw open circles on the -3 and 0. That means I do not want to include those values in my solution set. All right, next one. X is equal to 0.5. All right, if I plug that in, I'm going to once again plug it into the factored out form. And this is one of those problems where I'm not going to work it out all the way. I've got a positive times a positive times a negative. I know the answer is negative, and I know that a negative number is not greater than 0. So I know that because this is going to be a negative number, and it says, is a negative number greater than 0? I know it's false. So like I said, sometimes with this factored out form, it's just easier to be able to tell what the answer is going to be, you know, but without having to do all the work. So it sometimes saves you a little bit of time, you know. And the last one, x equal to 2. Let's plug that in and see what we get. 2 times 2 plus 3 times 2 minus 1. Is this greater than 0? So I get 2 times 5 times 1. Yeah, that's going to be positive. That's positive 10. And that is true because 10 is greater than 0. So we're going to highlight that in, and I'm going to put an open circle on the 1 because once again, we said that we cannot include those values of the critical numbers because this problem said strictly greater than. When is this function strictly greater than 0? And on all those critical values, that's when the function equals 0. Our final answer is going to be basically all that green highlighted stuff on the number line, but we're going to write it out in interval notation and set builder notation. Let's go ahead and do this. So the first one, let's do interval notation for our solution. It's going to be the open interval from -3 to 0, right? And then we're going to do union. Oh, I think I made a mistake there. Sorry about that. Our solution is going to be -3 to 0 union open interval from 1 to infinity. Or you could also write it in set builder, the set of all x such that -3 is less than x and x is less than 0. Or x is greater than 1. So either one of those solutions is fine. Yes. All right, let's go on to number 4. Actually, before I go into number 4, once again, let me just see if I can make this a little bit smaller so I've got a little bit more space to do number 4 here. It's just a little bit. I think that looks a little bit better. What do you guys think? Yes, I can hear your guys' answers. Yes, okay, so you guys agree with me. You guys think it looks better too. Excellent, I'm glad to hear that. All right, number 4. X minus 4 over 2x plus 4. When is this going to be greater than or equal to 1? So remember what our steps were. Our steps were we have to have a 0, right? And we wanted the 0 where, right? On the right. So I'm going to subtract 1 from both sides. Now, it also said that you needed to have a single, like, rational expression. Right now, this is 2 rational expressions, so I'm going to have to get a common denominator so I can write this as a single rational expression. So now I'm going to go ahead and I'm going to distribute that negative there. I'm going to write this as plus a negative, right? Because every subtraction problem can be rewritten as addition if we add the opposite. And now I'm going to distribute the negative to each one of these terms inside the parentheses. And we're going to have x minus 4 minus 2x minus 4 all over 2x plus 4. And greater than or equal to 0. Let's combine some like terms in the numerator. We're going to get negative x minus 8 over 2x plus 4. And when is this greater than or equal to 0? I'm going to factor this out a little bit, just so it looks a little bit nicer to me. I just think when I factor stuff out, it's just easier for me to see certain things here. So if I wanted to imagine the graph of this, I could already start seeing some stuff about this like very easily, especially when it's factored out like this. I'm basically going to take the factor in the numerator and set it equal to 0 and the factor in the denominator and set it equal to 0. Basically, this is telling me for the x plus 8 part when f of x is going to equal 0, and for the x plus 2 part, what values are undefined for this function. Because I get x equal to negative 2 here, and this is the value that will give me 0 in the denominator, this value is undefined. It's a restricted value. So I'm just going to write a little note here that for the domain, we're going to have basically the set of all x such that x cannot equal negative 2. Because I don't want to accidentally include this value of negative 2 in my final answer. Notice that the inequality says greater than or equal to. It'd be very easy to make a careless mistake and include this value in there if you see it as a critical number, because you might forget that it's undefined if you don't make a big deal about it, like I'm trying to make a big deal about it right now. All right, here's my number line. I'm separating it using those critical values at negative 8 and at negative 2. Notice I drew an open circle on that negative 2 right away, and I'm drawing a closed circle on negative 8. Closed because there's an equal sign. That means I can include that negative 8 because it can equal 0. Open on the negative 2 because it's undefined at x equal to negative 2. For my test points, I'm going to choose negative 9, negative 3, and 0. Let's plug those into the inequality and let's see what we get. I'm going to use the factored out form for the inequality here. So x equal to negative 9. And if we substitute into the factored out one, I think it's just easier for me to see the answers when I use that factored out one. I'm going to have negative times negative 9 plus 8 over 2 times the quantity, negative 9 plus 2. And we're trying to see if this is greater than or equal to 0. So negative times negative 1 over 2 times negative 7. What do you guys think? Do you guys think this is greater than or equal to 0? So I get negative 1/14. And is that greater than or equal to 0? No, that's false. I don't want to include that interval in my solution set, so I'm going to make sure I cross it out so that I don't accidentally include it. Next one, x equal to -3. So if I plug in a -3 every time I see an x, this is what I get. And it looks like this is going to end up giving me -5 over -2, and that's going to give me +5/2, and +5/2 is greater than or equal to 0. This is true. I do want to include this interval, so I'm going to highlight this in green and make sure I include this in my solution set. All right, last but not least, we're going to substitute x equal to 0. So if I substitute x equal to 0 into my inequality here, I get negative times the quantity 0 plus 8 over 2 times the quantity 0 plus 2. And we're trying to see if this is greater than or equal to 0. I get -8 over 4, and that's -2. -2 is most definitely not greater than or equal to 0, so this is false. I do not want to include that interval where the 0 is at. Our only answer here is going to be that green highlighted and that -8 that's included there. So the half closed interval from -8 to 2, or the set of all x such that -8 is less than or equal to x, and x is less than, I should have written -2 on both of those. I don't know what I was thinking.